Ladies and gentlemen, my subject is concrete properties, and I would like to present you, and it's a pleasure for me to present you in this session, the material models being included in Model Code 2010, and I will also show some practical applications on this subject. Well, if we look on the Model Code 2010, there we have in chapter 5.1 the material characteristics of concrete. And I have listed here what was the main objective of this chapter. First, we would like to improve the models from chapter 2.1 of the old Model Code 90, but the major target was to provide the designer with input data on material properties, first for crude estimates, for more sophisticated methods of design, and also for finite element applications. And also, we had to keep in mind that we had to look carefully on the input parameters which are known to the designer at the stage of design. We approached a holistic situation, looking to the whole construction life cycle in view of safety, serviceability, durability, and sustainability. And the material models cover all these aspects and deal then with strengths, stress and strain characteristics, time effects, temperature effects, non-static loading, and also the deterioration processes. Having this in mind, you can develop the contents of this chapter 5.1 concrete, and it is given here, and you will see that it starts with some general information, then the classifications by strength and density, then it deals with compressive strengths, tensile strengths, multiaxial states of stress, then deformation, meaning modulus of elasticity, then the stress-strain relations for short-term loading, time effects, temperature effects, properties to non-static loading, then the transport of liquid and gases in hardened concrete, and also with properties related to durability. First, let's have a look on the range of applicability. In the left column, you have here the criterion, and then what has been realized for Model Code 90, and then what is given in the new Model Code 2010. Concerning concrete strengths, has been already mentioned by Professor Walraven yesterday. The Model Code 90 only covered concrete strengths, mean concrete strength up to 90 megapascal, originally only 60. Now the new Model Code deals with high-strength concrete up to a mean compressive strength of 130 megapascal. Concerning the concrete type, not only normal strength concrete are dealt with, but the new Model Code is valid for high strength, for lightweight aggregate concrete, for self-compacting concrete, and we also tried to include as much as possible information which is reliable on green concretes. Concerning the concrete loads, it covers the same, both Model Codes, the old and the new one. That is the normal range where our structures are placed, and we have mainly temperatures between 0 centigrade and 80 centigrade. And we also tried to include information in those cases where we got it in view of tailor-made concretes. We made some references to important standards and recommendations. How this chapter 5.1 was developed. First, we started with a literature survey of the past decades. We prepared large databases, you will see some of them. We made a systematic analysis of the results. Then we evaluated existing constitutive models for concrete, and we developed new models where necessary. This work was primarily carried out by an FIB task group. It was task group 8.7, where I have been the convener. And we followed through our work one principal approach. this principal approach is briefly shown here in this very simplified equation. You have the concrete property described by any type of model, and if you have a different concrete, use the same basic model but modify the coefficients within the model. So this seems to be very important. If you look into literature, you find models for lightweight concrete, different model for high-strength concrete, again, different model for normal strength, every type of concrete, another model. And this we would like to avoid. Just one model and insert coefficients to deal with, or adjusting factors, I'm named it here, to deal with different time, with normal strength, high strength, lightweight, self-pour concrete, and ecological concrete. One constitutive equation for the behavior of different types of concrete. Well, I would like to move on to the compressive strength of concrete and the concrete grades, which is shown here. And as already mentioned, for Model Code 2010, it has been extended up to the concrete grade C120. What has been often asked in the past was how the characteristic strength is defined. And of course, it is a matter of the statistic, and it's plotted here on the bottom on the left-hand side. If you have the frequency over the compressive strength, you have this type of distribution. And if you look to the 5% cutoff, is a Gauss distribution. You have the factor 1.64 multiplied by the standard deviation. And if you look into the test data, you found that independent of the type of concrete, normal strength, high strength, or lightweight, the standard deviation is approximately 5. And if you multiply now this 5 with the 1.64, you end up by 8 megapascal. And this is a reason why in Model Code 2010 and also in Model Code 2019, there is given the basic equation saying the mean compressive strength is the characteristic compressive strength plus 8 megapascal. The background is the mean standard deviation for all types of concrete is round about 5. Well, in Model Code 2010, but also in the old Model Code, we had a function which indicates the time development of the relative compressive strength. You see here the function is an Arrhenius type function, is an Arrhenius-based approach. And on the right-hand side, you see the relative compressive strength plotted over the age of concrete. And you can see that this is that the formulas which are given in the new Model Code meet the experimental data we had available very well. This is based on an extensive database, and this is maybe also decisive for design, where you need design values and you have no possibility to do some tests. Otherwise, tests are always very good. If you look to the tensile strength, it is calculated from the compressive strength. You find here the formulas on the right-hand side. We had updated relations for high-strength concrete. We have two equations. This deals for high-strength concrete and this for normal-strength concrete. And we include also factors to deal with lightweight concrete, and also a factor which is important for tensile strength to calculate for mean, upper, and lower bound values. There are factors given for these upper, lower, and upper bound values. And in the case, these are the formulas you need to predict the tensile strengths from the compressive strengths. And these values are also included in the format of Shear and all the other things. But if you would like to predict, if you carry out tests, then we recommend in model code to run the tests according to a RILEM guideline. And if you do these tests on beams, you will measure the flexural strength, then you have a relation like this one here to calculate the tensile strength from the flexural strength of concrete. This is a relation taking into account a fracture mechanical approach. And we have also a new relation if you use Corres to determine the splitting tensile strength. You can calculate from the measured splitting tensile strength the tensile strength of a concrete, and we proposed a new relation, very simple, for the new model code. You have here the relation for the old model code. It was a constant value of 0.9. And in the new model code, we increased it a little bit because we found from test data, these are some test data from Müller. We did a very carefully survey of all the available data in the world, and we found actually there is a clear dependency on the compressive strength, like it is shown here. A is the ratio of the tensile strength measured in direct tensile test divided by the splitting tensile strength. But finally, the commission decided to stick to a fixed value. It is 0.1, and it is 1.0. And but on the left-hand side, on the commentary side, in the new model code, you have this more precise, this optimized prediction equation, which you might apply if you feel it is necessary. Also, fracture energy is an important parameter, in particular if you do finite element calculations. In normal cases, you need to give an input value for this fracture energy because it determines the strain capacity of your calculations if cracking occurs extremely. This is, in this diagram, there is plotted the fracture energy over the compressive strength. And here are included the old model code lines. And if you look to the old model code, you have a pronounced dependency of the size of the aggregates. The higher the size of the aggregates, the higher is the fracture energy. This was, at that time, it was prepared in 1985 for approximately to 1990. The first results we had on this subject. Now we have much more results on fracture energy, and we found that this dependency on the aggregate size is no longer right. And therefore, we dropped it, and we only have now one relation. You have it here on the right-hand side, this relation from where you can calculate the fracture energy GF simply from the mean compressive strength. This makes a big difference for calculations, which was only found by Dr. Cervenka when he ran the first finite element calculations using the old model code with the different values, and now the new model code, where you see a double, for example, of the fracture energy, a double of the fracture energy if you have only aggregate size of 8 or of 16 millimeter. But the new curve is the right one. Experimental data show that it is the right way to predict it. Multiaxial strength. This is a figure which I presented already more than 20 years ago when talking about model code 90. And at that time, we included the failure criterion from Ottoson to describe the multiaxial strength behavior from concrete. And we modified this model a little bit to make it co-type. And this type of modification we kept for the new model code, but we made some additional modifications to cover some inconsistency, to avoid some inconsistencies which had been included in model code 19. So the one was that we had not only the Ottoson model, but also we had given the Kupfer model because people were very accustomed to the Kupfer approach. So we had those both, the Ottoson and the Kupfer, but if you apply the Ottoson approach for biaxial loading of concrete to get different results than from the Ottoson. Now we skipped the Kupfer approach, we have only the Ottoson approach in it. And so we have one facial criterion for different states of stress and being valid for all types of the different concretes. And I show you here the predictions indicated for biaxial states of stress calculated from these models. And you have on the right side the different strength level, different concrete grades ranging from 12 up to 120. And you see the different curves for the different compressive strengths. And you have also this for lightweight aggregate concrete is included, so you can calculate multi-axial, three-axial, but also biaxial strength values from this modified Ottoson approach being updated for Model Code 2010. Another aspect which is important is the relation in view of stress transfer if a crack is opening. This is normally needed if you run a finite element program and you need to give the input data on this relation. And this was already included in Model Code 90. And also at that time, we found that the nick point is something by where we have 15% of the tensile strength. Now we modified it a little bit. We had much more experimental results now to compare with, and we said, okay, it is 20%. And what we also did, we had in the old model code this pronounced dependency on the aggregate size. We skipped it because we found nowadays from data the aggregate size has only a minor effect on the bilinear stress crack opening relation. This effect disappears behind the scatter of the individual data we had, and so we turned out to arrive with a formula which is simpler than the original one for Model Code 19. Then we have also to deal with the short-term loading, the stress-strain relation, and the triaxial concrete behavior. We did it not in Model Code 90. In Model Code 90, we had looked also to the biaxial behavior, stress-strain behavior of concrete. And in Model Code 90, if you remember, we modified a little bit the model of Darwin and Pecknold. But nowadays, more and more analysis is run by finite element, and so you need the triaxial and also the triaxial finite element methods are applied, and you need some guidelines. And we first had the idea to offer formulas, but if you would like to make it in the code-type version, it is impossible. It is impossible. It is such a complex material being developed the last 20 years that you can only find some major guidelines, but you cannot develop one formula like the Darwin-Pecknold formula, which we had earlier. If you look to the triaxial behavior of concrete, you have a strength increase for compressive loading, different tension and compressive curves. Very clear. You have nonlinear stress-strain response for tension and compression. You have a softening, decreasing stresses for increasing displacement. You have a localization, concentration of last range in a narrow band. And you have the dilatancy, inelastic volume increase near failure. In the Model Code 2010, we only presented generally accepted approaches of continuous mechanics on the right-hand side. No ready-made solutions are given. And if you read it, you need the basic knowledge on continuous mechanics. It is not possible to do it without it. And we give a variety of approaches applicable, showing the different, the mains are strain-based, isotopic damage, autotropic damage, microplane theory is cited, And on the left-hand side, we give thoroughly selected references to help the engineer to go through if he wants to get more into detail. And if you look now to the model code, this is just one picture of it. You see here on the left-hand side some commentaries, but references, the most important ones, on the subject. On the right-hand side, the basic formulas of the continuum mechanics behind these approaches. Though more was not possible to be offered, there may be another bulletin to be published to give a little bit more, but in a co-type format, you could not manage it different as we did it here in this version for Model Code 2010. I will now move on, coming to the deformation characteristics, starting with elastic strains and the modeling of elasticity. Of course, we apply Hooke's law, and this is a model of elasticity at the age of 28 days. You see it here for the strains. Hooke's law is valid, and we give again a basic relation being proved very well also for normal and high strength concrete, and to be calculated from the mean compressive strength, and we include the effect of the type of aggregate and also the effect of the unit weight. What is important in this context is shown in this diagram here. This is a stress-strain diagram for concrete. So if you have a loading of a virgin concrete and you do an unloading, suddenly you end up with some plastic deformations. I already said at this point, these plastic deformations will be tackled as part of creep. So if you run an analysis where you do not deal with creep, you need not the tangent modulus of elasticity, having no plasticity included. You need the secant modulus of elasticity, which includes some plastic deformation which initially occur at the first loading. And this is shown here in this relation. You have here the initial modulus of elasticity, or the tangent modulus of elasticity. You have to multiply it with a factor alpha to arrive at the secant modulus of elasticity. This is this one. And this reduction factor alpha is shown here over the compressive strength. In Model Code 90, we had just one constant value. It was 0.85. Now we have a transition from normal strength to high strength concrete. And if you have a concrete strength over around about 90 megapascal, then this factor is 1. You have no longer this initial set, these initial plastic deformations. Well, now coming to stress and time-dependent deformation. On the left-hand side is just shown what we observe in one test. And you have here the stress history on a specimen, or a set of specimens, and here the strains. We have first observing some strains occurring without loading, then we have a sudden increase of strains, and then we have a further increase of strains developing. And now, ladies and gentlemen, we are free to subdivide this observed total strength in different ways. And this is done in literature. We accepted that we term the first developing part as shrinkage. Then we assume that the shrinkage of the loaded specimen is the same than from an unloaded companion specimen. And we further assume that the initial elastic strain is constant during loading. These are major assumptions. And then we can define the additional strain by time, which is the creep strain. And I also indicate here the initial plastic strain is included into creep. And by applying this, we have now the total strain subdivided in shrinkage, initial elastic, and creep. We define a creep coefficient which gives the engineer an imagination of the magnitude of creep, and we define this coefficient as a creep strain divided by the elastic strain of a concrete at the age of 28 days. This is, we combine it with our modulus of elasticity, the initial modulus of elasticity. And we have also the creep function. Having a look on that, this is a quite different definition as, for example, Bazant has. Bazant skips the modulus of elasticity and speaks only of the J function, and, but you cannot see in his J function what is the initial elastic strain and what is the modulus of elasticity, and he has also no creep coefficient. We do it in that way. This is absolutely correct. There is no fault in it, but it includes the descriptive figures. Engineer knows, namely the elastic modulus and the creep coefficient. Well, this is very important to have a reliable deformation prediction. And so this is some example from Germany, a bridge which has been breaking down, and you can see very easy that the deformations being due to a wrong prediction of the creep is so excessive that the bridge has been completely rebuilt. So when modeling creep and shrinkage and the strain characteristics, we had to make some basic assumptions for the model code. And these basic assumptions are given here on the right-hand side, and again on the left-hand side, I show you the strain characteristics, but now at the stress impulse where I include the unloading where you have the recovery part. The basic assumptions are, we have a separation of total strain into shrinkage and load-dependent strain. We have a subdivision of load-dependent strains into initial elastic strain and creep strain. And we have included the creep coefficient to be defined as a ratio of creep divided by the elastic strain at the age of 28 days. We have made simplification. We have said that the initial plastic strain, we deal it as a viscous strain, it's part of the creep. And we have neglected largely the nonlinearity effects to keep the models simple. And if we deal with linear creep, then we have to accept Boltzmann's principle of superposition. This means that at variable loadings, we have to accept this type of integral equation to describe the effects of creep and also of shrinkage. Result of linearity. Very often we have been asked, why do you define the creep coefficient in the way creep divided by elastic strain of the age of 28 days? The Americans do it in that way, the ACI, creep divided by the elastic deformations at loading, and not at 28 days. The explanation is given on the left-hand diagram. Creep coefficient over age of loading, the most decisive parameter. And if you plot now for the same concrete, the creep coefficient of ACI and that of FIB, you see the difference. There's first of all no difference for the age 28 days, which is clear. But if you reduce the age of loading, you have a maximum for the ACI definition, and then it goes back. But every engineer has a feeling that the creep is the higher, the lower the age of loading. This is only be correctly reflected by this type of approach we adopted in the Model Code 90. If you adopt this type, the engineer get confused. And so we skipped it and stick to the old version of definition, and by the same time we also include our well-defined modulus of elasticity at the age of 28 days. This is the background of this different definition to the others. Well, further we have to think about how we define creep. Now we said, okay, make it as easy as possible, just predict the mean cross-section behavior, knowing very well that creep is different over a cross-section. Assume linearity between stress and strain and only allow for a simple approach for nonlinearity. Separate the deformation components due to conventions and physical validated characteristics. And then also a very decisive point, which parameters should be included? We decided to include only those which are known to the designer. This means that the compressive strength forms the substitute for the composition of concrete. And, well, the range of validity are according to the practical conditions on site, types of concrete, environmental, and so on. Well, and then if you look which type of model you choose, we selected a linear product type model concerning the conservative approach with an integrated summation of deformation components reflecting physics and kinetics of the deformation characteristics. Well, those models have been developed, as I mentioned, on a literature review. We developed computerized databases. We then derived the models, improved models, obeying the rules or the principles of constitutive modeling and physical approaches. And then we did the optimization. We did a nonlinear optimization with all those models. We had an Marquardt-Levenberg algorithm working very efficiently with such complex model with a lot of parameters to be optimized. This optimization and the background is shown here in this figure where I have plotted strain deformation over time. And you see here, for example, the test data and some regression line which may be hand smoothed. Then we calculated the deformations for certain points in time being equidistant in a log scale for the time development. This gives some more weight to longer ages of observation, but this is reasonable. You have to make a decision. And then we calculate the deviations between our model and the real test data. Then we have a last square fit. We sum up these squares of deviations, and then we divide it by the mean deviation. And though we end up for one experiment for a coefficient of variation, and now we have to integrate them up or sum them up of all the different experiments, and finally we end to an optimized, to an overall coefficient or mean coefficient of variation. And we also look to a mean prediction error. This means we look to the average deviation for our prediction at a certain point in time. And the optimization procedure consists now that we have to minimize this coefficient of variation. And we did it with our models and the database. We minimized it. And now, if I show you this on the left-hand side in a model code, given the coefficient of variation, this actually means the prediction accuracy of these optimized models. In literature, sometimes you find comparisons of different prediction models, and the comparisons are based on the calculation of coefficient of variations. You will never find such a comparison from me, because it is completely unfair. People optimize their own model and use a data set to compare it with the other models. It is ridiculous to show such comparison. It makes no sense. You could only compare it if you make the optimization of all the different models with the same data set. Otherwise, forget it. Don't believe in any comparison of prediction model of accuracy if they are not optimized on the same database, having a Marquardt algorithm in the back and these formulas. We wrote it very clearly in our bulletin and the background. Well, Now, after all these introductions, very quick on the constitutive modeling of shrinkage and of creep later, you have the left-hand side, the simple approach of the model code 90. Now we had to extend it to basic creep and to dry creep. This was necessary in view of the pronounced shrinkage we observe for high-strength concrete. First, if you look for normal strength concrete, you see that the drying shrinkage is last, and the basic shrinkage observed when you have the demolding point at 1 day, something is very, very small. It is only, let's say, 5% of the total shrinkage. So this basic shrinkage was neglected all the time in earlier approaches. But now, dealing with high-strength concrete, this basic shrinkage becomes rather high, and you cannot no longer neglect it. So you have to deal it separately, and this is be done in this approach where it is subdivided in basic and in dry shrinkage, as it is shown here, the new approach, which is now found in Model Code 2010, being developed within FIB already in the year 2000 and also published. Constitutive modeling of stress linear creep. I already mentioned various types of approaches. When accepting linearity, this basic Volterra equation is valid. We have our definition of the creep function, reflecting creep coefficient and modulus of elasticity. And we can develop from this equation an algebraic equation according to Drew's procedure, which was finally a little bit refined by Stanek Besant, but it is the same equation. But what is decisive, ladies and gentlemen, is which type of function is here in the creep coefficient or the creep function. And there we have only two basic approaches, different approaches. This is a product type, where we have a product of age of loading and duration of loading, and we have the summation type, where we deal with delayed deformations and the flow deformations. Some of you will remember that the Model Code 78 had such an approach, but we now adopted this product type approach for the new Model Code, and it was also included in Model Code 90 for some reasons. And you have also keep in mind that within these different types of approaches, from the constitutive point of view, you may include, of course, a separation of total creep into basic and drying creep components. If you compare now the constitutive modeling for Model Code 90 with that of the new Model Code, you find the separation in basic and drying creep, which was necessary to be able to deal with high-strength concrete. And now we also have no longer the uniform deformation characteristic. We have a deformation characteristic following physical principles. And we have, for the time development, it is shown here, for basic creep, a logarithmic functions. Please keep in mind that this logarithmic function has no finite value. If you run it in a computer program and it doesn't take care of the duration of loading, you will end up at infinite values of the creep. You must be a little bit more careful. But I show you that this type of approach is the best one. And we have, again, the drying creep. Of course, drying creep ends if there is no difference in moisture between the environment and the concrete. Drying creep stops. And what may look a little bit tricky for you is this exponent. In the old Model Code, it was 0.3. Now it is dependent on the age of loading. And the big advantage is that we can avoid some deficiencies of the old Model Code. First, see the time development. You have here for basic creep, the log lower, only log function, which is a very straight line, very long durations of loading in these tests, over 13 years. And if you add up the logarithmic and the hyperbolic, this is basic and drying creep, you cover very well these curves for a dry ambient environment. Well, if you need a prediction of creep recovery, you have to apply the principle of superposition, as shown on the left-hand side. And if you do it with model code 90, you end up in this curve. You have a strain reversal, which is wrong, which is a weakness of the product type approach. Now we modify this product type approach by this exponent I mentioned, and you get the absolute right prediction of grip recovery, so having a linear model. Normally you only cover this with a nonlinear model. Now we have a linear model covering this interesting aspect. But we knew it already for model code 90, so we said you can model code 90 apply for recovery only in combination with the age-effective method. Prediction of relaxation, left-hand side definitions of creep and relaxations. Right-hand side you see the prediction of the model code 90. For some very seldom cases you have a change in sign of a stress, which is illogical. Not nice. Not nice to have. It only happens very seldom, but it happens. But now we managed to avoid it completely. You can apply the principle of superposition. You will get no change in sign. Model code 90, we had only to accept the age-adjusted model that matters. Then you could do without such change in sign. Well, the formulas on the left-hand side are a little bit, right-hand side are a little bit complicated. In many cases, it is enough to do with a simplified approach. So you have here given for different concrete grades, the CT20, 315, and C100, the shrinkage design values. And you can also see that they vary not so much, for example, for the different concrete grades. The parts are different. Basic and drying are different, but the sum is not so different as you can see from these figures. Well, and also for creep design, we have the long version on the right-hand side in the code, but also a table on the left-hand side. And this table is also published in Structural Journal, the background paper on chapter 2.1. Also here, the C20 to C100 design values for the creep coefficient, and you can see how large is a span. For example, it ranges here in this table from 7.7 up to or down to 0.4. This is round about 20. So it makes a big difference which are the boundary conditions for your structure concerning the magnitude of creep. Fatigue behavior is also dealt with completely new, and I can now a little bit quick over because this slide has already shown by Joost Walraven. He took those slides from me. You have here the new approach. You see comparing the both figures, the differences, and what is also, and also shown by Joost Walraven, very important that we also modified the design value for the fatigue behavior. And the reason is very easy to see here. This is a design value of the old model code. If we would kept the same, we would not take profit of the increasing strength. We had to modify it. And we now modified it. It is now this curve. Oh, sorry, go back. It was going too much. It is this curve, which is now valid, but there is some room for improvement, or on the other, or say otherwise, this is additional safety for fatigue, which is now included. These basic formulas, I think they have still to be improved in the future. Impact loading, we had in the old model code the effect of the strength. You see here the effect of strength on the relative strength increase due to the rate of loading. If you look to this large scatter of experimental results, you see there is no really identifiable effect of compressive strength. So we skipped it. You have just one line. You see it here for model code 90. Makes it easier. So only one relation for normal and high strength concrete. Then we dealt with the temperature effects. You have here on the left-hand side the compressive strength dependent on the temperature, on the ambient temperature, the compressive strength in the hot state. You see the scatter of the data, but you see also the model code curve. It indicates you the general tendency. On the right-hand side, you see the compressive, specific hot compressive strength over the compressive strength. And you found that the reduction, it is plotted for 100 centigrade, is round about the same for all types of concrete. You have a clear dependency of the temperature, but no dependency of the compressive strength. And this is the same holds true for the modulus of elasticity. Left hand shows the effect of modulus elasticity. We gave different functions for normal strength, high strength, and lightweight aggregate concrete, and for normal and high strength concrete, and different one for lightweight aggregate concrete. And this is shown also on the right hand side, where it is again plotted the specific model of elasticity over the compressive strength. Well, there are some more relations. I skip it here, otherwise I would speak too long. I move on now to my last part, that is aging and durability. We had to model the transport characteristics as a basis for estimating the durability. And we also dealt in new model code with durability-rated processes. This is carbonation, ingress of chlorides, freeze-thaw degradation, alkali reaction, degradation by acids, and leaching processes. And the models which are presented allow for design for durability for different types of concrete, different probabilistics. I will show you a practical example. Inspection management and also life cycle management is possible with a relation given in Model Code 2010. You have here, for example, the diagram showing the diffusion coefficient depending on the compressive strength. Of course, compressive strength is a very crude measure of the microstructure of the concrete. So you have a scatter, but there is also nevertheless a clear trend, and this is met well by Model Code 2010 relation. You find here the relation on the right-hand side given here. In the old Model Code, it was just a constant value. Now we modified it to cover also with high-strength concrete. Well, we looked also for formulas for water permeability to make possible similar calculations. You see the coefficient of permeability over the compressive strength. Again, the both lines for Model Code 2099 and 2010. Of course, an improvement for the new Model Code. Again, for gas permeability, same principle. The coefficient plotted over the compressive strength. Comparison of the old and the new model. Please see there is, in fact, a large scatter, which actually means that the compressive strength is a crude estimate. But it is the only one normally the designer has at the stage of design. Well, and also for capillary suction, we have a large scatter band if you plot the coefficient of water absorption over the compressive stress, but you find these relations in the new Model Code, allowing the engineer to estimate how the capillary section is dependent from the compressive strength. Well, and now you can do calculations at different levels of accuracy. You have here the chloride corrosion, for example. On the bottom, you have the degree of deterioration. You have an initiation period, and the propagation just starts when the chloride concentration at the steel is sufficiently high. And then the corrosion starts. This is our critical limit state. And the time which elapses until this start is described by a diffusion law, and this is the resolution of this diffusion law, this equation you find in the Model Code. And then you can calculate the time until a critical value of the chloride content is achieved at the steel, at the surface of the reinforcement. The same for acid attacks, but we have no initial time. It immediately starts with degradation, but we have given on the right-hand side formulas to describe the corrosion by an acid attack. You can clearly calculate it, what will happen in the next years if you have an acid attack by a certain value for the pH value and what is going on in the future. The carbonation process, my last example, we have also initiation period and then a propagation period, and we give in the new model code a more sophisticated model for the carbonation, for the propagation of the carbonation front. You see here, don't go into the mathematical details of this square root formulation, but you can see that the carbonation depth is calculated from the environmental function, from the execution, then the inverse carbonation resistance, a very important parameter which may be measured on site, the CO2 concentration, and also a weathering function is included. And we did this complicated approach to allow for a full probabilistic design approach. And I will just explain you very briefly the differences between the old concept we had, the descriptive one, and now the performance concept. In view of durability, we had assumed we have here the actions and the resistance, and we assumed that our concrete will withstand all the actions over 50 years. We had so far no clear idea what about the safety margin. It was our experience. And this experience you find given, for example, for a certain ambient conditions. We said, okay, if the maximum water cement rate of the concrete is 0.6, minimum strength C25, minimum cement content, and the concrete cover is 40, then this building withstands the actions of the environment over 50 years. No possibility to calculate anything, just feeling. Now, we have the same approach, but we have included probability. You see, here again the resistance and the actions, but now they are functions of time, and they are statistical parameters. And we have, for example, here, if our resistance is a concrete cover, it is of course constant with the age, but the actions are moving on, and both are scattering, and we have an overlap zone, and we have at a certain time, when both are overlapping, a corrosion can start. And now we can calculate it very exactly with this type of model because they are based on a statistical concept. I have to admit that so far we have only consolidated models for carbonation and chloride ingress in the initiation phase. We have no conclusive models. We have some ideas about for frost, acid, and bleaching attack and alkali correction, but they have not been developed so far that they could be included in Model Code 2010. And if you now do a design with the complete model, I do it for carbonation-induced corrosion. Now this is your design approach. You have the concrete cover as a resistance. You have the carbonation progress. This is the equation I explained already. You have the failure probability and your reliability index. You transform it because it's better to speak of reliability than of failure probability. Reliability sounds always much better than failure probability, but it is the same. And then you have to verify it, and you end up, if you run the calculation with a different software which is available in the market with such a type of function, where you have the reliability index over the age of the structure. And of course, the older the structure, the lower is the reliability index, and you end up with a design situation, and the owner of a building may define the risk he is ready to accept, and this gives this defined service lifetime, and you can adopt the concrete that you just achieved your design target beta value at a certain time. And if it is carried out, I will show you a very simple example of a tunnel inner shell. Very simple example. This is the inner shell of a tunnel. It gives you the boundary condition saying intended lifetime is 100 years. The target reliability index is beta 1.7, which means round about 5% of damages to be accepted after 100 years. And the limit state is defined as that time when the depassivation and the reinforcement starts. Now, this is a design situation. You have here, I see the concrete cover calculated for 55 millimeters. The standard deviation was 8 millimeter. The reliability index, as said, was 1.7. And the failure probability 5%, as I mentioned, after 100 years, design stage. Now, for example, after having the building, the tunnel realized, you do some measurements, and you find that the concrete cover is in the average 55 as planned, but due to poor workmanship, your standard deviation is higher. And now you can easily calculate the consequences. If the standard deviation doubles from 8 to 16, you reach your limit state already after 60 years, which makes a big difference instead of 100 years after 60 years. Or vice versa, if, for example, you have a good workmanship, low standard deviation, but by some error, your cover was realized 1 centimeter too low, you also end up already after 60 years, 62 years, at your target reliability index. Or, on the other hand, after 100 years, your damages are not only 5%, but 15%. So now you have a tool to calculate it. Before, you have no chance to do it. Just a simple example how you can work on that. Full probabilistic design, according to Model Code 2010, acquires sophisticated statistical software. This is available, but it needs some experience to do it. So we need simpler formats, and so simpler formats are on the way to be developed with partial safety factors or simple tables and diagrams. I constructed, for example, one example for a simplified ad, and I did it that way. You see here, for example, with regard to carbonation. I divided my concrete into 3 different categories: low, medium, and high carbonation resistance. And I also now offer in this table the service life. Vary 50 or 100 years, like you like. And I also vary here the reliability index, how much damages you are willing to accept. And then you can calculate the concrete cover meeting these boundary conditions. See, this is completely different as we have it before. And now you can say, okay, but where I can take this carbonation resistance from? Though the answer is very easy, you should take an easy measure in a laboratory. It costs not more than testing a cube. Or you can use a diagram which we have published in the background document, where you have this carbonation resistance over compressive strength. But you see, over a large range of compressive strengths, you have the same carbonation resistance. This means the compressive strength is not a good measure to calculate for it. But a test helps you very much, and you end up with a complete different table giving exact values on your reliability and on your service life. And the same can be done for the chloride ingress. So there you have decisive the diffusion coefficient. I here subdivided 3 diffusion coefficients: high, medium, and low. And again, service life 50 or 100 years, the designer or the owner can decide. You have reliability index, how much damages you are willing to accept. More 10% or 5% only. Then you can calculate your cover necessary, and I give 3 examples in the tables. Rome, Italy, warm in summer and moderate winter. Climate, of Karlsruhe, the city in Germany where I'm coming from, different than the one of Rome, and the hard climate in Moscow. And now you can calculate the concrete cover. Now you see, for example, if you have a high diffusion coefficient and the climate in Rome, you end up with a concrete cover of 138 millimeter. If you have a low diffusion coefficient and you are in Moscow, it's only 25 millimeter. And it depends also, of course, on the safety limits. So completely different tables will come up, helping the designer to introduce the service life, if it's 120 or 50 or only 20 years, make a big difference. It can be carried out. Again, if you don't like this measurement, which is behind on the left-hand side, you can make an estimate from the compressive strength, the diagram, right, compressive strength over this diffusion coefficient. But as you can see here, you have to accept this scatter. Compressive strength is a crude measure of the diffusion coefficient. You have this, have to be this in mind. It is a first approach, but not the best one. Well, I end up now with some conclusions, and I give you an overview of what is included in the chapter 5.1, concrete in the new model code. I had to take out only a few examples, otherwise I will stand here not only for 1 hour and for 2 or more hours or days. What is important, it is valid for normal strength, high strength, lightweight aggregate concrete, and also, of course, self-compacting concrete, and also some formulas are given for green concrete as far as it is reasonable. And what is behind these models we developed, and it is now available, a bulletin giving the background information on the formulas. Right, the time when the model code is released, there is a document where the designer can find the background of the formulas given in chapter 5.1 of the model code. I would like to thank you for your patience and your attention. Thank you.
Thank you for such an excellent lecture. In one of your slides, you have shown that if the standard deviation is more than how the design service life can be calculated. My question is, the entire formulation in the model code is based on mean strength, where you have assumed that it is 8 MPa plus the characteristic strength, which means the standard deviation of 5 has been considered. Now, the design normally is, preceded by the construction, and suppose the construction quality is not good, and the means, because it is basically by the characteristic strength, which means the mean strength required was much more. You have designed it for, say, 100-year design life, but at the end of construction, you found that actually you have gone for only a service life of 60 years. What is your comment? Do you think the formulation should have been based on characteristic strength? That would have been more appropriate?
So the formulations which are given in the model code from the material side to the design part are consistent in itself, absolutely consistent. The characteristics strength is the design parameter first, but in the formulas, there is calculated with, or included the mean compressive strength which may be tested. What you mentioned is the effect of poor workmanship on the construction site. You can never make prediction models to cover with this. You can make models taking into account certain basic deviations which will occur. But it is impossible to calculate at the design stage already with very strong deviations. You must assume that the deviations from your model prediction are the ones which are included at the stage when the models have been developed.
But this factor, there can be a possibility of radiation in the standard deviation at site, where this cannot be denied. Is this factor in some gamma form in the form of some partial safety factor?
It is included. Yes, it is included. No? And also, for example, we're giving in this chapter 5.1 variation coefficients. No? And there you have, for example, let's say for creep, there is a variation coefficient of 25%. So if you have a creep-sensitive structure and you do the calculation, you may do it with the upper and lower bound value. And you can easily calculating from assuming a Gaussian distribution from the coefficient of variation, your higher and your lower bound value for the creep coefficient. It is no problem. In many cases, on the left-hand side, the information is given to deal with the scatter which is in the material. But if you are uncertain, and there is also a clear recommendation to do some tests. So that's large bridges or tunnels cost millions, billions of dollars, and a test of shrinkage and creep may be 10,000 euro, and you have the full sketch and have a perfect model of the behavior of your particular concrete.
Sir, I have a question regarding the creep estimate of concrete. In a practical situation, if you have a bridge using pre-stressed concrete girders and a reinforced concrete slab on the top, and suppose at a point of, at certain point, you load the structure, what happens to the reinforced concrete portion of the slab is that it gets loaded, and then the creep effect will start increasing those deformations of the reinforced concrete slab. As far as the girder below is concerned, it is not a case of further loading. It's a case of further unloading. Because in a pre-stressed concrete, the girder is already very highly stressed in a compressive situation, and when you put a load on it, the pre-stress starts getting reduced. So it's a case of unloading in pre-stressed concrete girders. When you are actually physically loading it, the concrete is getting unloaded, and therefore the creep coefficient in case of recovery, its case of recovery of creep is at a different rate than that at the reinforced concrete portion. Now, we are, even at present, are unable to make a distinction between in real calculation in that, because the code doesn't give the different coefficients for the loading and unloading part of it. So does the model code 2010 give any method of doing that?
Yes.
Yes.
Yes. Right for this case, you are recommended to apply the principle of superposition. You have the loading phase, and after pre-stressing you have the unloading phase. And you can apply the principle of superposition to get an estimate of the concrete behavior. And it works. You can do it on the principle of superposition, the Boltzmann principle I have shown to you, but you can do it also in a simplified way, as in many cases it is done, applying the age-adjusted modulus methods. And this includes the relaxation coefficient of the algebraic equation I have shown. And this relaxation coefficient can be taken from tables taking into account the different load situations. There has been developed a CEB manual. This number is 213 or 14. And in this bulletin, which was worked out primarily by Mario Chiorino from Italy, there you have the relaxation coefficients for different types of loading. And you can include them in the algebraic formula to calculate for those effects. Or, on the other hand, you can do it exactly, for example, in the finite element analysis, with applying the principle of superposition, using the original formulas. It is possible.
Thank you.
While discussing on creep, you have introduced the terminology drying creep. And also you have said it is stress linear creep. So even drying creep is also stress dependent. Can you explain it further? Because drying shrinkage is understood, but drying creep is something new to us. Can you explain it further?
Well, if you observe creep characteristics and you do tests in a lab, and you have sealed specimen, which in reality would be a very thick member, a sealed specimen, which loses no water during loading, it shows a creep. But as it loses no water, we term this basic creep. If the same specimen, same concrete, same age at loading, but unsealed, water is given to the environment. You subtract the deformation part from drying shrinkage, but you found then an additional creep, much higher than the basic creep. And this creep, we termed drying creep. This is the additional creep which is observed when a member or specimen is drying out while being in use. And to be able to model the different effects in the right way, because the drying is a diffusion-driven process. And so we have to separate it from the total creep. We say total creep consists of two components, the basic, which occurs independent of the environment, and the additional term, which occurs related to the thickness of the member, the environment, and so on. And this is a logical approach. It is physically based, makes predictions more accurate, is a little bit more complicated. Concerning linearity, it is in fact that the basic creep is highly linear, while the drying creep component is linear, starts to become nonlinear, starts around about a stress level of 30%, which means the stress divided by the strength at loaded up to 30%, you get some nonlinearities. But in predicting, in the predicting formulas, we skipped it. Otherwise, you get very complex formulas, and you can no longer apply this type of Boltzmann principle of superposition, which makes life easy. We are, as engineers, we are assumed to adding up linearly our different components. And if you deal with nonlinearity effects, you may no longer add up linear the parts. And, but the errors you make in the normal range of loading are within the scatter you have to accept. So this simplification, I think it is acceptable.
Yes. Thank you very much. Last question, please.
Thank you. Sir, you were saying this model is validated for the normal state, high strength, and lightweight aggregate, but you are not talking about a high performance concrete, because in high performance concrete you are using the different cementitious material, just like the fly ash, silica film, and GGBS. This showing the influence of the creep and shrinkage very different manner. And I saw there is no provision for the high performance concrete. Have you any incorporated these things in?
Yes. So I have been talking this hour also always on normal strength and high strength concrete, but only in terms of the compressive strength. Yeah. I explained also why I did it. Of course, we did detailed investigations, how the effect of silica fume, how the effect of fly ash may be shown or included. For example, I could show you a lot of diagrams. There is no clear effect on the inclusion of silica fume. Of course, you increase the compressive strength by the amount of silica fume, but this may be well described just by using the mean compressive strength. You did not know the additional information that it is silica fume or not with silica fume. So it is clearly shown in diagrams being behind, and you find those diagrams in the bulletin 70 of FIP. And also with fly ash, so first, the designer at the stage of design, he knows the strength, C80, great. He doesn't know the composition of the concrete. This is mostly the thing which is fixed very, very late. Yeah? So it makes no sense to make a prediction based on the silica fume content or on the fly ash content. And on the other hand, their effect is covered reasonably well by the compressive strength. I could show it in diagrams, and though this gave us the right to skip it, to make this easier for practicing engineers.
Sir, my last question. You are saying this model is developed based on the standard data banks. But which standard data bank you have used? I don't have any idea.
Which data bank?
Yes, creep or shrinkage, related to creep or shrinkage.
Yeah. We have used our database, which we developed together within the TG 8.7. So the basis was the Rylam database, the earlier, which has been developed by me when I did my PhD 35 years ago. And then we included more and more data. But we selected very thoroughful, because we are doing a lot of measurements in our lab all over the year, and have much experience on that. Not every published data will be included. And of course, it also makes no sense to include as much as possible. It is explained in more detail in the Bulletin 70, because it is much better to cover all the conditions which you have in practice, well distributed over all the boundary conditions. And not having, let's say, hundreds of test results, where the diameter of the specimen is 150 millimeter and the ambient environment is 65. This brings an optimization just to this point, but does not cover all the conditions which are relevant in practice. So we established an own database, being behind this model and taking all up the experience we made about this. And well, you can try it with, Basant has now published a new database with a lot of experiments. And I'm not interested in it. I did some tests with my doctoral students, and there are so many areas where there are a lot of tests which are out of any interest of practice. So skip it. I do not optimize the model on these tests.
Thank you, sir.